Assalamualaikum dear students. Last time we were discussing continuous function in topology, and today I want to give few more examples, and I want to discuss these examples in a similar fashion that we were used to discuss in real analysis. But there are few different things that I will discuss during the solution of these examples. So, first example is, suppose f is a function from a topological space X, where tau x is a topology on X, and y tau y. This is another topological space, and tau y is a topology on Y, and you are defining function that fx is equal to c, any constants, any constant. So now I want to check whether this function is continuous with respect to this. So what was the idea? Last time we have established a theorem that whenever you want to show that your function is continuous, you have to take, if you are taking g belong to tau y, then you have to show that its inverse image. From here, you have to show that f inverse g belong to tau x. Because you know that in continuity we want to preserve the neighborhood. So that's why if g is in some neighborhood of tau y, then is g is in tau y, then its inverse image f inverse g should be in tau x. This was the result that we have deduced from the definition of a continuous function. Now to onward, I would prefer to use this result because this is a little easy than that typical definition of continuity. Okay, now since function is a constant function, so you take any set g belong to tau y. So that's why there would be two possibilities. Because this is the image value c, and certainly c would be in y. So there must be two cases, whether c belong to tau y, g, or c does not belong to g. Okay. So by definition, let g g belong to tau y. You know that your function is f from x to y. Your function is f from x to y, and here your x, whatever x is, so its image is fx, which is equal to c. Here is this. Now this is your c. So there is a question whether your c belong to g, or c could be here. Either c belong to g, and if this is not c, then c does not belong to g. So I have two possibilities, right? So then either c belong to g or c does not belong to g. Because you are taking g, any arbitrary element of your tau y, and you know that you have just one image, which is your constant, that is c. So that's why there is a possibility that c belong to g or c does not belong to g, right? Now if c belong to g, if c belong to g, then by definition, if c belong to g, then by definition, what is your definition? Your definition is fx is equal to c. Your entire domain is giving you c, corresponding to every value x, because your function is constant. When function is constant, this means that corresponding to every number x, you are getting the value c. So this means that fx is equal to c. So then by definition, fx is equal to c, or you can say that f inverse c is equal to x. And if c belongs to g, then certainly f inverse g, because g has one element, that is c, because function is constant. You have no element here in your y, because y is containing just one element. So that's why this implies that you can say that f inverse g is equal to x, which is belong to tau x. Hence f inverse g is open, right? So if you are taking c belong to g, then of course then by definition fx is equal to c, or you see that f inverse c is equal to x, because c is the only element of g, because g is an open set in y. That's why you can say that f inverse g is equal to x, which is an element of tau x. Hence your by definition f is continuous. This implies f is continuous since g was arbitrary. Now the second case, if c does not belong to g, secondly, if c does not belong to g, then of course g must be equal to phi set, and so because f inverse g must be equal to phi, because you know that f of phi is phi, and f inverse phi, you know, those elements of x which are mapped onto the phi set mean that they are not other than c. So because all the elements of x are giving number c, that's why there does not exist any element of x which is mapped onto the phi, and that could be the phi set itself. That's why. So since no element of x, since every element of x is giving you answer c, whenever you take x belong to x, this implies fx is equal to c. So this means that the subset of x which is not giving the answer c could be the phi set. Could be the phi set. That's why f inverse g is equal to phi, and you know that phi also belong to tau x. And again, the inverse image of your member of tau is in tau x. That is the inverse image of g, where g was an element of tau y, is in tau x. Hence in either case, so I think we should not write here, because here still you have to discuss the second case. Now these were the two possibilities, that either c belong to your desired your chosen open set, that is member of tau. If you take any member of tau g, then of course there are two possibilities, either c belong to g or c does not belong to g. Now if c belong to g, then what is f inverse g? Of course this must be capital X, because all the elements of x are mapped onto c. Now if c does not belong to g, then of course which are the elements, which are the subsets which are not assigning the number c, and you know that all elements are assigning c, so this may be the empty set, right? So in this case f inverse g is equal to phi, which is also in tau x. Hence in either case if g belong to tau y, then f inverse g belong to tau x. That is f is continuous. Okay, this is our first example. Now I have another example. If you take let tau be a usual topology. Example number 2. let tau be the standard topology on R, and F from R to R is defined as Fx is equal to x mod. Then again F is continuous. For this you have to see that corresponding to every open set, here I am taking the same topology. Tau is the usual topology. Tau is the usual topology, and you know that what are the members of usual topology. These are in fact open sets, and these are in fact the union of open intervals. In particular, every open interval is also a member of your real line R. Okay, so you know that in real line we like to take intervals. Intervals are in fact the open sets. Okay, so you take an interval AB. So let G is equal to AB. You take an interval AB belong to tau on R. You know this is tau on R is equal to basically usual topology. So I am taking here tau on R is equal to in fact tau U. That is the usual topology. And you know that if you are taking set of real numbers, and that's why we will take some intervals, because all intervals are in fact the open sets on this topology, right? Because our topology is the standard topology, or sometimes we call usual topology. So if you take an interval AB, so can you find what is the idea is to find its inverse image. What is the inverse image for which the answer is this? So you can calculate this. Look at here. This is your function. This is your function fx x mod, and here say I am taking here a. This is my a. This is my b. Similarly, here I have here is A, and here is B value. The answer of A is A mod. Answer of A is A mod. This is in fact A. This is A, and the answer of B mod is B. This is your B. And similarly here you have 0, and here you have minus B, and here you have minus A, right? So for this the answer is again A. This is your A. Like this is your function is this. Look at this. Now look, this is A, this is B. At A my answer is A, and at B you put here B. This is B mod, answer is B. But here I have another interval. If I substitute minus B, then again answer is B. At minus B I am getting answer B. And if I put minus A mod is equal to A, then again I am getting A, right? This length is A. So I have two intervals. One is minus b to minus a and a to b, right? For which I am getting this interval. So whenever I take some interval AB belong to this topology, that is a usual topology on your real numbers, then you could have two intervals and in fact their union. And you know that since it is a topology on the set of real numbers, so that union of n into intervals must be in usual topology as well, because you know that the union of any number of members of ta is in ta. That's why this is an open interval and this one is an open interval. That's why their union must be in this ta, right? So this is the set. So here you can say that f inverse g is in fact, what is this? This is minus b to minus a union a to b. You can write like this. Okay. Sorry, f inverse of this set. Right. This is f inverse g. So f of this set is, in fact, you are giving AB. Okay. Either you substitute this interval here in fx is equal to x mod, or you substitute this interval, you will get AB open interval, right? So this implies that f inverse AB open interval. What is this? This is in fact f inverse g, which is equal to minus b minus a union AB. And what is this? This is belong to tau r as well. That's why you see now again what I am doing. I have taken a function f from R to R and I have defined this function fx is equal to x mod, and here since these are the same sets, so I am taking a topology which is, you know, that the standard topology or usual topology of intervals on the set of real numbers. Now I want to see that whether this function is continuous with respect to usual topology. So the idea is you take an open set from here, because topology is same. That's why I am taking G is equal to AB from tau R, topology on R. So now I need to check whether its inverse image is also a member of the same topology. This is my idea. So for this function, I must to know the set for which this is in fact the image set, right? So if I see the graph, you know, my graph is this x mod, and see, if I take minus b to minus a, then again I am getting value a and b, so the interval AB. Look, this is your a, this is your b. So I am getting this interval, and this is, what is this? This is a to b. And if I take AB, then again I am getting this interval, this is a to b. This height is a, this height is a, and this height is b, in fact. So that's why you see that I have noticed the interval, in fact the union of two intervals, that is minus b to minus a and union a to b. If I apply f on this, I will get this interval. And what was this? This was your g as a member of tau. So that's why you see f inverse of this, what was this? This is f inverse g, and this is in fact this interval, which is the union of two interval, and you know that union of any number of members of tau is always is in tau. That's why this is an element of tau r. Hence, what can I say that since this was the arbitrary open set from your topology, that was the usual topology, and corresponding to some arbitrary interval, you are getting a member of the same topology. Hence, f must be continuous. This means that this implies f is continuous. Now instead of using this, I can have some more examples. If I take the same function from R to R, and I am taking the same topology, example number 3. This is example number 3. Say fx is equal to ax plus b. Now I have a straight line. Is it continuous? Now here my function is again from R to R, and I'm taking the same topology, that is the usual topology. And with respect to that topology, I have to check whether this function is continuous. Here you can say that a is not equal to 0, right? Okay, so see, again, similarly, I am taking that G is equal to AB. This is some your arbitrary interval belong to tau R. Now I need to find whether there is some interval for which this is the image. The idea is to know the points for which this is in fact the image. You can do this by using some calculation as well. If you put A here, if you put here A, so what will happen? Fx, Ax is equal to B, you need to find the value of x. So x would be equal to minus b by a. X would be equal to minus b by a. I am using a and b here, so I should change this as pq. pq, right? So you can calculate. I have changed a b here with pq because I already have chosen a and b here in this function. That's why I am changing my interval ab to pq. So first you put p here. Then if you put here p, f of p, what is this? This is in fact ap plus b. Okay, so if I take fx is equal to p, this is your fx, this is my first point, p. I'm sorry, this is ax. So for this p, I want to know that what is the value of x for which p is the image. So see from here, p is the image. Can you find x from here? Yes, I can find. So x would be equal to p minus b is equal to ax. So x would be equal to p minus b by a. This would be the point. Similarly, can I find a point for which q is the image? So this means that q is the image of your fx. This was ax plus b. Am I right? So from here you say that q minus b would be equal to ax, and from here x is equal to q minus b by a. Right. Yes, I can find these 2 points, q minus b by a and p minus b by a, for which you are getting this interval. This can be viewed through this graph as well. So let's draw its graph. Okay, so where is this straight line? Let's say I'm taking this straight line here. Say this is the straight line. Of course, this is your B. This is your B. And here you take some P and Q. Where is P? You take some P and you take some Q. Let's say this is my P and this is my Q. You know that we like to take our interval PQ along y-axis, because this is in fact the image set. PQ I am taking from PQ from this set. You can say that say this is R green, and say this is R red, R yellow. I can label this. This is R green and this is R yellow. But for R green and R yellow, you are taking the same topologies. That is the usual topology, and you are taking this from R yellow. R yellow. This is topology on R yellow, right? So PQ is in fact on the in your range set, and you know that we like to plot our range set along y-axis. That's why I have taken PQ. This is my arbitrary interval, and for sake of convenience, I am taking both the points, positive points. Okay, so here you see that if I see this one is my point for which I am getting the value P. And what is this? This is in fact my point where I am getting P answer is if you take P, this was P minus B by A. This point is P minus B by A, right? Similarly, if I take Q, this is my Q, and Q is meeting here, right? This is the second point, and this point was Q. This is the Q length, this length is Q length, and this length is P length in fact. So Q length, Q is the answer when Q minus B by A, and this point is Q minus B by A. Yes, now you can understand. I need to know the points, I need to know the interval for which this interval is the image, right? So I can say, you can say from here very easily that here f of P minus B by A to Q minus B by A, this is in fact, this is your PQ. You can check, this is so easy. If you substitute this interval, P minus B by A, put here P minus B by A would be cancelled, B would be cancelled, the answer is P. If you put this, you are getting P, height P, and if you put this here in this function, you will get height Q, right? So this is the interval for which this was the image. And other words, or you can say that F inverse PQ is in fact this one, P minus B by A and Q minus B by A. And look at this, this is also belong to tau of R green. You know that I have taken the same topology on both red green and red yellow, right? So just to understand the idea of domain and range, otherwise both are the real numbers, and I am taking the usual topology on set of real numbers. So this is very much clear. Now you see that this function fx ax plus b when a is not equal to 0 is in fact continuous on the set of real numbers, two real numbers with respect to usual topology. So in this way I am not finding any difference between the usual definition of continuity in real analysis and the continuity in topology. But I may have many examples for which the same function may not be continuous when I change topology. So now I am going to elaborate these type of examples where I am taking a topology, let's say tau1 on first set and tau2 on the second set. Then I have to define some function. So with respect to those different topologies, again I need to check whether your given function is continuous or not. So let's have few more examples. Another example is you take a different function. So let new example. You take let tau1 is equal to, I'm taking tau1 is equal to a topology that is minus a to a, where a is greater than 0, a belong to R, union phi and R. This is a topology. What this topology is, I am taking intervals minus a to a, where a is any real number, right? This is similar to the last topology that we have taken in the form of intervals. But here is a little difference between, always you need to show that one number is negative and other is positive, and if you want to show that an interval is a member of this topology, then you must have to show that it is of the type minus a to a. So this is a little different than that one, because there I was taking the interval AB, I was not setting any condition on A and B, but here this is a little tricky, because I am taking intervals of the type. Here this is 0, this one is say minus 1 to 1, this one is minus 2 to 2, this one is minus 3 to 3, like so on, so on. So whenever you have to show that a member is a member of this topology, you must have to show that it is of the type. I mean, it can be expressed in the form of an interval, and that interval must be of the form, I mean to say minus a to a, one thing, or it is phi, or it is the real number itself R. So these are the types of open sets that I am taking in this topology, tau1. So take another topology, say, and I am taking tau2, that is equal to 0, and then A, you know, this is half open, half closed, like this, and here again A is greater than 0, A belong to R, and union phi R. This is my second topology, and this is a little better than the previous one, in a sense that whenever you want to show that a member is a member of this topology, you have to show that this is of the type, means 0 is in closed form, and here should be any interval which is open. Like if I say that I have this 0 to 2, whether this is a member of this topology, no, this is not. This is not. 0 to 9, yes, this is a member of this topology, right? So in fact, I am taking members of the type. I have 0, this is 0, and 0 is closed. Then I take this, and so on, all these. So members of the type, the collection of members of, so whenever I take a member from T2, this must be of the type, or it may be phi, or the set of real numbers itself, right? Now, with respect to these two topology, I want to define few more functions. Okay, so let's define f from x star 1 to x star 2, or star 1 R2 by, say, fx is equal to minus x. Okay, I think I have to replace my marker. Okay, so if I take a function from tau 1 to tau 1, tau 1 to tau 1 or tau 1 to tau 1, fx is equal to minus x, we will see that it is continuous because let g is equal to, you have to take, here tau 1 is like this, if I take g is equal to minus a to a, some interval belong to tau 1, then can you find out what is the number for which you are taking minus a as the image? By putting here, you will get a. For a, you are getting minus a, and for minus a, you are getting a. This means that your image set remains same. Okay, so for this, because if you calculate here, f of a is equal to, in fact, minus a, and f of minus a is in fact a. Anyways, if you put this in the form of interval, then of course we like to write the lower one first and then a. So from here your interval must be minus a to a. This would be the interval, which is in fact the same interval. That's why if you take this, then of course obviously f inverse g must be equal to minus a to a as well, which belong to tau of tau r tau 1, which belong to tau 1 as well. Hence this function is continuous. So whenever you take any point from tau 1, it must be of the type in corresponding to this function. You see that our image must be of the type again, and which is belong to tau 1 as well. That's why your function must be continuous, right? But instead of tau 1, if you use tau 2, right? Next example, if I take tau 2 to tau 2, next example, instead of tau 1, if I take tau 2 to tau 2, your function, and taking the same function, then this function will not be continuous, because you take, let g is equal to, in fact now is of the type 0 to a. If you put here corresponding 0, you are getting 0, and corresponding to a, you are getting minus a. This means f of 0 is 0 and f of a is minus a, and from here the interval must be minus a, because a is on the open side and this would be open, and 0 is in closed side and this must be 0. In fact, this is the interval for which this one is the image, right? And you can say that corresponding to this g, this one is the image, or its inverse image is this, because you need to know that the interval, the member of tau 2 for which this is the image. Then clearly f inverse g, which is equal to f inverse 0a, and what is this? This is equal to minus a to 0, and you know whether this is a member of tau 2. Tau 2 is of the type 0 is on closed sides and a is on open side, and here what I have, minus a to 0, and this is not in fact a member of this. Here a is positive as well, so this does not belong to tau 2, right? This is not a member of tau 2. Hence f is not continuous. See, I have the same function, but I am changing the topology, and by changing the topology, we have seen that continuity is hiding, in fact. So a continuous function may be a discontinuous function when you are changing your topologies, right? So this function is not continuous because this is your the image set, right? Because we need to know that function for which this is the image set G. So this is interval for which this one is this one is the pre-image. Hence this means that since this is not belong to tau2 as well, that's why this function is not continuous. This means that f is not continuous with respect to tau2. Okay, I can have another function that was that we have discussed. I can change the function as well. If I take fx is equal to x square, now I am taking from tau2 to tau2, fx is equal to x square. Now you take a point, okay? You take a point of this tau2 and you see whether its inverse image is in tau2 as well. So let G is equal to 0, A. You know, this is belong to tau2, and I want to see that what is the image of this set. You know, if you put here A is equal to x square. If you I want to know that what are the numbers for which A is the image. You know, if you take 0 is equal to fx, then you know x square is equal to 0, this implies x is equal to 0. But if you take this A is equal to fx is equal to x square, A is equal to x square, you will get x is equal to plus minus A square root. Right? So these are the two numbers. This is minus A square root and plus A square root. And for 0 you are taking 0. That's why your interval must be minus A to A, because I need 0 as well. 0 is here and I need to know that the number for which 0 is the image is 0 itself in fact. And for minus A, if you put minus A square root here, then again you are getting A, and if you put A square root, then again you are getting A. That's why from these information, this is in fact an interval minus A square root to A square root, right? So here we see that, note that f of g is in fact f of 0a. If you find this, what is this? This is equal to in fact minus A square root to A square root. Okay, you can calculate this. Corresponding this, the value of 0 is 0. Here you have in the center of this interval, and corresponding to A, since A is on open side, that's why the values corresponding there is A square root and minus square root. That's why I am taking both as open. So this is an open interval, right? And this implies that f inverse minus A square root to A square root. So f inverse G. Sorry, I'm saying that in fact f of minus A square root to A square root, this interval is in fact 0 to A. You see, corresponding to this entire domain, which is a member of tau 2, which is not member of tau. This is in fact the member of tau 1. Corresponding to this, you see, corresponding to A, you are getting A, corresponding to A square root, you are getting A, corresponding to 0, you are getting 0, and all the values, since it is x square, all positive value, so corresponding to this interval, you will get this. So from here, f inverse 0A is in fact minus A square root to A square root, which does not belong to tau 2. Look at. Again, this function is not continuous. This function is not continuous. Right. And if I take tau 1 to tau 2, then this must be continuous. This function is continuous if I take tau 1 to tau 2. Okay, so if I take this is not tau 2. Now if I take this function f from r tau 1 to r tau 2. Now look, I take this from tau 2 and this belong to tau 1. This belong to tau 1. Now in this case, this function must be continuous. Look, you have the same idea, but this one belongs to tau 1. If you take tau 1 to tau 2, then this is continuous. This must be, this must be, and f is continuous. But if you take tau 2 to tau 2, then this is not continuous. Then this is not continuous. And also, if you take this function from tau 1 to tau 1, now then again it would be continuous, right? So what will happen if you take tau 1 to tau 2? Now again, take this function from tau 1 to tau 2. Like right. So this was the idea. Similarly, you can check what happened from tau 1 to tau 1, and you can swap these by using tau 1 to tau 2, then tau 2 to tau 1, tau 2 to tau 2, tau 1 to tau 1. You can change your functions as well. Right. So my agenda was to show that you may have some functions which are continuous with respect to one topology, and soon after they are discontinuous with respect to another topology. So with the help of these examples, I was in fact elaborating the ideas. Okay, now I have one more example which is also very interesting and easy. So take another example. So x is equal to a, b, c. Say this is your a. Take a is equal to a, b, c, and define a topology on a is tau a, phi a, and you take tau a is equal to phi a, and a, then c, then ac. Yes, it is a topology, you know. And define a function f from r to a to r, where you know R is the set of real numbers, and certainly I am taking a usual topology on this set R, where tau on R is equal to usual topology, and define function f from a to a by f of a is equal to okay, I want to take function from R to A. I'm taking function R to A, and I can define explicitly fx is equal to A when B and when C. So this is my function is when x is less than 2, say when x is less than 2. And secondly, I have 2 less than equal to x less than equal to 3, 2 less than equal to x less than equal to 3. And for C, I am taking x is greater than 3. X is greater than 3. Now, I have to check whether this function is continuous. if corresponding to every open set, if corresponding to every open set, its inverse image is open in R with respect to usual topology, then this must be continuous. So see here, you see F inverse phi, you know this is phi belong to tau of R, and you know F inverse X. What is F inverse X? Because this is A. You are taking from A to R. So F inverse A, this is in fact X belong to tau of R. Now I have to check whether corresponding to these open sets of tau A, whether their inverse images are open. So what is F inverse A? Look at this. F inverse A. A was when X is lesser than 2. So F inverse A must be equal to mean this. So for which I need to know those values for which you are getting image as A. This was X is less than 2. So its answer is minus infinity to 2. Yes, this is F inverse A. And what is F inverse C? What is F inverse C? When you are getting value as C, you are getting C when X is greater than 3. And I want to find F inverse of C. This is F of C, and F inverse C is the X values. And what are the X values? These are the X values. So this is in fact greater than 3. So 3 to infinity. So F inverse is 3 to infinity. This one. Yes, this is belong to tau R. This is belong to tau R. The last one is AC. I need to know that what is this? You have F inverse A and F inverse C. So F inverse AC is in fact the union of these two. And since both are belong to tau R, so their union must be in tau R as well. Hence F must be continuous, right? Okay. Also, F inverse AC, I want to this. This is in fact minus infinity to 2 union 3 to infinity. Because corresponding to this, when you apply F on this, you are getting A. When you apply F on this, you are getting C. And if you apply F on the entire union, you will get AC. And what is this? Since both are the members of tau on real usual topology, so their union must be belong to tau R. This implies F is continuous. Now we have completed almost all type of examples. So far I have elaborated in detail. From here now you can have better idea that how we understand a continuous function in a topological space, right? You could have a function from a discrete set to your real numbers, or you can have a function from real to real. So whatever you are taking, you can enjoy the last theorem that I have established in my last lecture, that from the definition you can deduce that a function f is continuous if and only if g is a member of tau y, then its inverse f inverse t must be a member of tau x. Okay, I have some more interesting things which are in fact the remarks. Few remarks. Okay, here I want to elaborate 3 remarks. One is, if X is a discrete space and Y is any arbitrary space, X is a discrete space. I mean here tau x is equal in fact power x, and Y is any space with respect to any topology, tau of y. Okay, if you take x as a discrete set and y is any topology, whatever you are taking, we are not concerned, right? Then f from x to y is always continuous. This is true because whatever you are taking y from y, if you take g belong to y, tau y, of course g is getting some members under your function f. So their images, inverse image, since x discrete space and you have tau x, all every possible subsets are the member of tau x. So whatever you are taking as an image, its pre-images, the set of its pre-images is a subset of px, so must be a member of tx, member of tau x. That's why this is in general true that if your x is a discrete space and y is any other space, whatever it is you are taking, you are free to choose. And let's try this. But there must be a function from x to y. If f is a function from x to y, where x is a discrete space and y is any other space, then this function must be continuous all the time. Right, this is my first remark. My second remark is, okay, if number 3, remark number 2, here if you are taking x as a discrete topology and y be an indiscrete space, so let x be any topological space and y be an indiscrete space, right? X be any discrete topological space. X is any discrete set with some topology. Let x, you take any x which is a discrete set like ABC, 1, 2, 3, whatever you are taking with respect to any topology, and if you take y as an indiscrete space, you know what is indiscrete space? This is a topological space where you are getting just two members, one is y and other is the phi, right? This means that tau y is equal to phi and y. Then f from x to y is always continuous. Why this is happening? Because you are taking f from x to y, right? If you take phi, then phi, f inverse phi here, f inverse phi is equal to phi. This belongs to your tau x. And if you take f inverse y, so I think we can relax the condition. Let x be any topological space rather taking discrete set. Probably you have to say this. So I'll check myself also. So I think we can free the condition. Let x be any topological space and y be an indiscrete space. Here you have fx is equal to y. In fact, the mapping is this: fx is equal to y. So f inverse y must be equal to x. This belongs to tau x. That's why. Now, since phi and x are always the member of tau x, that's why the condition may be relaxed, right? Okay. So if you take y as the indiscrete space, then this function is always continuous, whatever you are taking the mapping is, because phi inverse y must be phi and phi inverse y must be x. Okay. Similarly, the first remark was, if you take x as a discrete space, I mean to say that topology with the help of power set, then y is any other space, then this function always be a continuous function. Similarly, if you take y as indiscrete space, then again this function must be continuous. I have another remark. Third one is, third remark is, f from tau 1 to tau 2, f from x tau 1 to x tau 2 is continuous if and only if, this is a characterization as well, if and only if tau 1, tau 2 is a subset of tau 1. Tau 2 is a subset of tau 1. Means that tau 1 is stronger than tau 2. Tau 1 is finer than tau 2, right? So these are the three remarks so far I have stated. We will check this remark in our next lecture as well. And till that, you try to understand the definition. In the next lecture, we are going to elaborate some theorems related to continuous function in topology. Okay, thank you very much. Allah Hafiz.